I'm probably the first presenter in this entire conference who's using the back button on one of these on their first slide. So about me, I'm Ali. Alizishaan, if you ask my mom, like the long-ass name. I'm from India. I live in the San Francisco Bay Area, and I'm employed as a machine learning engineer. That's what pays my bills. Okay, title slide. Let me tell you a little story, right? My company is in the business of building chat applications for banks. Yeah, sure. Okay. Oh, thank you. So my company is in the business of building software for banks. We build a chat application that bank agents use to chat with bank customers, right? Now, I am employed as a machine learning engineer, and what do I really need? What do I really need to do my job? Number one, data, right? And being in the banking industry, regulations are hard. We generate a lot of data through the chats, as you might imagine, right? On a daily basis, people are chatting with agents, we're generating like volumes of conversational data, but we're not able to do anything with that because of regulatory constraints. So now, you kind of run into this situation where you have a bit of a chicken and egg problem, right? To be able to build any sort of machine learning-based features for your system, you need data, right? And in this case, since there's people's social security numbers in there, there's people's addresses in there, there's people's names, phone numbers, email IDs, all of that in there, to be able to use that data becomes difficult. So we basically need machine learning to be able to get data for machine learning, right? So it's a bit of a chicken and egg problem that we've encountered, but we managed to do some clever machine learning and use proxy data or synthetic data to be able to build this system or get started with this system. So at the end of the day, we decided we're going to build a system that creates periodic copies of our chat data with sensitive information masked or redacted, right? So if you say, hey, Ali, my phone number is 123456789. 10, or not 10, but 0, right? The typical American phone number format. Now, that data, what we do is the system would basically transform that into, hey person, my phone number is phone number. So replaces the actual value, or the actual sensitive value with a generic placeholder. And then you can replace it with randomly generated value. So it can turn into, hey Tom, my phone number is 732, blah, 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 whatever, right? So you can also, to make it look more natural, you can also do that, but you've basically de-identified the users, right? And you've still preserved the data in the form that it was in. So product people come with a bright idea. They're like, let's create periodic copies of a chat data with information masked, and they wash their hands of it. They're like, okay, cool, done. Then it goes over to the data scientists. The data scientists are like, easy peasy, let's just use an NER model to detect the sensitive entities, and then just, once you've detected those entities, just replace it with the generic placeholders. Now, this means the problem's solved, right? The talk is done. We can go home early, do whatever, eat, drink. Then come the developers. They're like, you've given us so much stuff, but we don't quite understand it. Like, what do we do with this information? How do we build software that serves the supposedly amazing science that you've given us, right? And there's the ops folk. The ops folk are like, how do we deploy that? How do we deploy software that doesn't exist? Or how do we deploy science? So they are stuck in a situation where they do not know what they're dealing with. Like, it's complete chaos. So the good news is, and something that engineers can build off of or work off of, is that engineers don't usually have to care about how a model works. Engineers pull out one of the tools that engineers are in a position where they can pull out one of like the most powerful tools in their toolbox, which is abstractions, to get rid of this issue. So for an engineer, so what does a model mean for an engineer, right? Like an engineer can understand a model to be a set of mathematical equations. So treat it as a black box. Think of it as a set of mathematical equations that does something, right? Does something. You don't care what it does. You don't care how it does. You don't have to get involved with it. All you care about is it's a black box. It's a system that accepts a certain set of inputs and generates a certain set of outputs, right? So as an engineer, you can treat it as that. So now then, at the end of the day, your job then gets reduced to produce output by computing these equations in some way. You don't build those equations. You don't worry about those equations, nothing. All you care about is how do we use these equations to compute outputs for a certain set of inputs, right? Now, if you just take what I've said, right, and if you compare it to what an engineer does on a daily basis, when an engineer is building systems, we're not doing anything that's any different from what I just mentioned right now. We compute outputs for a different set of inputs. If you're building a web API, you're like, for your REST input, or some outputs pass through you through a REST API, you're just processing them and returning an output. So machine learning, again, gets distilled down to regular software engineering, right? Now, once we've brought it to that level, the machine learning specific bit is that we just need to take that, like we need to learn how to manage that file of equations, or that equation, that definition of equations that the data science people have created, and only what they understand. Like as engineers, we don't need to get involved with that, but only what they've created, we can just work with that. So they give us a file containing all the magic math that exists in there. We don't care about how that works, right? We just care about how to manage these artifacts, how to load them, how to run inference on them, and use them to compute the outputs that we want to compute. Come on. Okay. So in order to understand what we're dealing with, we just need to, like, it's a 101 slide, just understand what it means. We don't need to get into what model does this, how this works, nothing. But what is NER, or named entity recognition? Named entity recognition is basically if you say Ali works at Coney in 2019, you just transform, like, it's a process which will say Ali here is a person, Coney is a company, and 2019 is time or year or whatever entity name you choose. So that's all we need to understand about the machine learning, and that's where the machine learning in this slide ends. Okay, so what software are we building now? The question comes, what kind of software are we building, or what sort of constraints are we building software for? We need to have batch processing of inputs. We're going to have bursty load patterns, and we need reliable delivery, right? Like if an input is triggered, we need to make sure that the output is present. So now, a lot of people in the room who have any sort of data engineering experience whatsoever, and even some engineers who don't, the first instinct would be, that sounds like Spark, right? That sounds like something that you can do, solve easily with Spark, right? But now picture this. You're working at a small startup. You have millions of things to take care of. You have like 50 million things on your to-do list, and you have time to do 5, right? Do you want managing Spark clusters on a daily basis to be one of those? Do you want to be spinning up, spinning down Spark clusters, or paying for very expensive software that does that? The answer for us was no. I mean, if your startup has had a lot of funding and you just want to create the illusion of doing work, but for us, that was a real challenge. For us, we had like a lot of things to do, and we figured that this is not something that we want to spend a lot of time on. We just want to build it and forget about it, right? And the bursty load patterns bit in there, right, kind of give us an idea. What if we tried to do this in the most counterintuitive way possible? What if we tried to do this using a serverless offering? So we decided to go out there and start experimenting with function as a service offerings. So If you're on AWS, it's AWS Lambda. If you're on Azure, it's like Azure Cloud Functions or something, GCP, Google Cloud Functions. Every major cloud provider has a function as a service offering, right? So we decided to architect the solution to this problem using function as a service offerings. Now, why is it counterintuitive, or why is it, a tough sell to go with function as a service offerings as opposed to just working on regular bare metal machines or like Spark clusters or something like that, or tested solutions like that? Execution time limits. AWS Lambda has limits of, I believe it's 5 minutes now. So 300 seconds, 5 minutes. And then they've increased it to, so back then it was 5 minutes, but now I believe it has been increased to 15 minutes. You have memory limits, right? So you can only use a certain amount of memory. Your function or your code can only use a certain amount of memory, like a fixed amount of memory. Does not scale with anything. It's like a hard bound, right? It's like hard RAM on a machine. You cannot increase it. So you have like a hard memory limit. Then the code package that you send in, right? The code package has certain deployment size limits. Then you have limits on local storage. So smart people in the room might be thinking, yeah, if you have memory and if you have unlimited storage, try, cycling through it and just do something like that. But even that is restricted. And number 4, cold start times are high. So basically what that means is that the first time that you call that function in a given time period, it'll take longer than what you expect it to or what it does in the average case, right? So that is what a cold start is. And those times can be pretty high and they can, impact the overall performance of your system. So we decided that we're going to go with a serverless implementation of the software solution, and we came up with like a very simplistic architecture where you have function 1, which pulls from a source database and serializes those records or passes that records across multiple copies of function 2 in a request-response model. And once it has the process records in it, it just dumps that to the target database, right? Very simplistic end-to-end system. Anybody in the room have any idea of why this might not work? Or what constraints would we be limited by? Can anybody think why this might not work? Or why is this a bad idea? Sure.
Because 20 seconds to get my model up, and it's 1 giga of memory size, so I can do that.
Okay, so memory. Okay. Any other inputs? Memory is one. Any other? Okay, I'll save myself some time. So this only works if size of your model plus framework, right? Alluding to his point about memory. This only works if the size of the model, like the set of equations that you've built, plus the framework that you're using to compute that model. So both of them matter because you cannot just like consume a set of equations and not have some library to compute it because you need both, right? So this only works if both of them are less than the packet size. Here we chose to go with a lightweight framework, Spacey, but you can use TensorFlow or whatever, like pick your poison of choice, right? Your call. TensorFlow, PyTorch, whatever you want, you can use that. So you have a model binary, which is like 90 MB in this case, and that is something that data scientists have given you, and you do not have any idea of what's in there, so you cannot tweak it, right? That's a given. You cannot play with that. The framework, on the other hand, is something that is more up your alley than the model itself as engineers. So it's something you can tweak with, but what you see here is 302 plus 91 MB is significantly greater than the 250 MB of uncompressed, and I repeat, uncompressed memory that AWS offers you, right? So the deployment package has to be 50 MB, and you can uncompress it to a maximum of 250. So those are the constraints with Lambda. So this itself exceeds it. How do we go ahead? The idea is going to fail. Come on, okay. So then bright idea number 2. What if we were to download the frameworks plus model at runtime, right? So we distribute our memory footprint or our memory requirement between like the local storage that's being given to us, the actual memory or RAM that's being given to us, and the stuff that we can push in through the deployment package, right? So deployment package has a 250 meg limit. You have about 500 MB of local storage, which you can leverage for runtime. And you have your RAM itself, so you can put some, you have about, at best, you have 300 MB of, 3000 MB of RAM on AWS Lambda that you can use in the peak setting. So you have these three things that you can, distribute your workload across and get things done. We're not going to play around with memory. We'll just use the deployment package and the local storage. So architecture 2, right? Similar to the previous one, the only modifications being that now we're at runtime downloading from a model artifact store to temp storage. So now each time function 2 is run, you have data that will be picked up from the model artifact store and written to temp storage. Do you guys see any sort of problem with that here? Or any sort of constraints again? What? Yes. So now, high resource cost, right? Models and artifacts are downloaded each time the function is run. So if you look at this architecture, function 1 is calling multiple copies of function 2 at each time, right? So if you have 1 billion records in function 1, and if function 1 is calling like, I don't know, 10,000 copies of function 2, your model artifacts are being downloaded 10,000 times. Now, that is anything but efficient, right? Like, you're going to spend a few minutes that you're going to get billed for each time your function runs to download that file, and that is not acceptable. That is an inefficiency. And how do we work with that? So one of like the gray areas of working with function as a service offerings is that they're marketed to be stateless services. And for the most part, they are. But there are some hidden caveats that are not recommended for use. But if you know what you're doing, you can really leverage them to do good stuff. So for example, what really happens is the values that you once write to temp, and if the function exits successfully, the next time it's called, that value or whatever you've written to temp will still be there. And that is because of how Lambda works behind the scenes. So what we can really do is we can warm up the function before we use it. And what I mean by that is we can just have a dummy run once, download whatever model, whatever artifacts we need to temp. And now on the back end, right, AWS would have created a container image, and you've written that value to it, and that container is now kept alive. It's not killed, it's kept alive because AWS typically in practice, we found that it kills Lambda containers after about 30 minutes of inactivity. So the container has been created, the value is written, right? So now, what if we could warm it up before we use? So now, if you call the function 1 billion times, it's not going to download it 1 billion times. So in this architecture, if you call function 2 1 billion times, it's not going to download it 1 billion times because the container is warm. So it's already accessible to the local code. So if you can build in logic to not download it so many times, you're saving substantially on over 1 billion calls. You're saving 1 billion times whatever 3 or 4 seconds it takes to download it from over the network, right? So that is one way in which you can optimize stuff. Smart packaging. Make your deployment packages as small as possible. Just put in as little as you need, And what you can also do is, if you trim it sufficiently enough, the one time you're downloading that heavy payload, it'll take lesser Lambda runtime to successfully download or successfully complete that network transfer. Now, packaging tips. Know your framework really well, right? With Spacey. So when we started with Spacey, Python being an interpreted language, unit tests are in the code base. At runtime, you don't really need unit tests. Unit tests are for the development phase of it. When you're using a framework or when you're using something, you don't really need unit tests. So you can safely delete them. Now, if you understand the Spacey framework, if you go into the details of the Spacey framework, you find out that it contains a lot of model artifacts. Like Spacey has been created for multiple languages, and it's designed to work out of the box for multiple languages and for multiple NLP tasks. But it turns out we don't need all of them. If I'm building a system to parse English text, I don't really need Chinese or Russian or Japanese language models to be in there because I'm not going to be using them. Does that impede Spacey functionality? Yes, but it is functionality that I'm not using, so I can safely delete it, right? So we took a 300 MB Spacey binary, we deleted the tests, and we brought it down to 300 MB. And then deleting unused language models helped us, wait for it, bring 300 MB down to 15 megs. I don't know what percentage that is, but that's pretty damn huge. Another packaging tip that you can use, but I would not outright or very openly recommend it, is to compile your code base to PYC files. What that does is each time your Lambda function is invoked, it saves the time the Python interpreter takes to convert your Python files to PYC. So if you just directly run PYC files, you're shaving off a few milliseconds off of your actual runtime. And that is a direct cost saving, but it is kind of sketchy or not a very recommended move because it can make your code notoriously difficult and hard to debug or trace. Right? So if you're fairly confident that your code works and everything, you might want to take this step, but I would not take it right away. So how do we build our code, right? We come up with like a Dockerized build pipeline, and the reason for doing that is because a lot of Python, a lot of like the lower level, like Python relies on a lot of lower level C code. So what is compiled on your operating system might not necessarily work on AWS Linux, which is AWS Lambda's real time, or whatever cloud platform you're using. Your cloud platform's underlying operating system might not necessarily be the same as your developers or your build server's operating system, right? So you want to be able to make sure that you're creating a Docker container to create that virtualization or to simulate that operating environment. Only add codes that's needed. Understand code base and delete tests, which is what we went through. Now logging. This is something that I'd like to touch upon because if you remember, data privacy was a major concern when I started this talk, and it still remains one, right? But we still want auditability as engineers. We want to make sure that what we've built runs and runs as predicted, and we want to be able to audit our performance. So how do we do this? Each time we start doing something, each time the system begins, or at any point, right? The request at its first entry point is assigned an ID. And then we use that ID to track that payload throughout the process or track that invocation throughout the process, right? And each module logs I/O. Each and every module of the code, each and every sub-module logs I/O, like logs whatever it does on your cloud offering. But here now you have the problem of privacy leakage. Like if every module is logging all the payloads that it sees, then if you log, let's say, my name is Ali, right? And my number is whatever, the example that I used earlier. You've leaked data because now your logs actually contain that PII, right? Even though your chats might not, but your logs do. So you've leaked PII. So a way around that was, what we figured was to have that ID intact, but replace the payload with a hash of the payload, right? So now hashes, by definition, are irreversible. So you cannot extract the payload back from the hash, but you still know that it's still repeatable because if you know that it failed on data records 5 to 500, you can repeat that invocation on 5 to 500, and the hash will remain the same. Unless somebody's changed the database, well, then you have bigger problems to worry worry about than this particular program. So this is the final architecture that we settled upon. You have a cloud-based trigger, so like an alarm or something that at the hour triggers that function. That function pulls from the source database, writes to the target database, and then sends payloads to the model inference function, sends multiple records to be masked to the model inference function. The model inference function basically pulls from the artifact store, pulls the actual model or the set of mathematical equations from the artifact store, uses that to compute outputs for the inputs of function one, and then function one just writes the process outputs or the masked records to the target database or target output source. So systems ready to use, problems solved. Questions?